All right, guys. Check on the group, please. You all got it? All right, so let's begin. So we want to take a look at oscillations, and you want to look at a special type of oscillation called a simple harmonic motion. All right. So let's just do a quick little run through what an oscillation is, and then we will move into simple harmonic motion. I'll show you a simulation, so you'll observe everything operates. Yeah, I think I just sent it back on chat. All right, no, this is the old one, the one you all have already. So what's an oscillation? An object which continuously moves to and fro is said to oscillate, and the motion is said to be periodic or cyclic motion. I didn't send it. I'll send it as well. Right, each to and fro motion of the object is called a cycle of oscillation. I did try to send it. Maybe it didn't send. Yeah, I did try to send it. I'll try this now. So an example, a simple pendulum, right? A simple pendulum, mass on a helical spring, a molecule disturbed by a sound wave or a vertical rod in a zero viscosity liquid. All of these will oscillate. All right. There are a few things that we must have in an oscillation. Number one, it must be able to store potential energy, and it must be able to obtain inertia. So that potential must always be converted into kinetic. In case you forgot, kinetic is what again? Energy due to motion, and potential is energy due to position. All right. So let's take a look at this here. There's this nice little simulation that shows you simple harmonic motion, right? Right, we'll do the physics just now. Let's take a look at a pH. Right, what you see here. Here we have an object, right? And the object has a mass. Does this object have the ability to store charge? I mean, to store energy? Yeah. Yes. As I move away here, look at the graph on the left side. Look at the graph on the left. As I move away here, what type of energy is increasing? Potential energy. All right. So therefore, this object has the ability of storing energy. Right? Can it now create inertia? Let's see. Yes, it can. So if you look closely there, there's a constant change between the green and the blue. You see enough? Once an object can do that, it means that the object oscillating in the layer. Right? Oscillating. So there we have an oscillating object. Right? It's not too smooth for all there, but it's oscillating smoothly here. Right? So it's oscillating smoothly, and there's a constant change between kinetic and potential. All right? I'm not sure if you're seeing it there. I'm going to try and pause it in the middle. Okay, that was bad. I will try again. Bad. We can get it there. Anyway, look at that point there. That point there is mainly what? Mainly kinetic with a little bit of. What about there? More kinetic, less potential. So it getting close to being what? Equal, right? So what is, you all may not be seeing it there, but what is, oh, let me make it bigger there, right? Right? That green and blue, the sum of that is called your mechanical energy. So mechanical energy is the sum of the kinetic and potential. Right? Quick question. When is the potential the largest? On the well, the highest point, right here. Almost get it. Right, but it getting close to it, right? Oh yeah, I can just slow it down. Right, so if you look there, we will stop him here. Where is max kinetic? Huh? In the middle, right? That's max kinetic. Max potential. Max kinetic. Back to max potential. All right? You're seeing that? So that is basically an object undergoing simple harmonic motion. Right? Y'all think you can sketch the graph? Could you sketch the graph of kinetic and potential as it moves from maximum displacement? Can you sketch the graph? Try it now. Let's do a quick little sketch. Let me just lay the foundation here for you. Right? Actually, I can do it like this for you. Right? See if you can sketch what the kinetic energy might look like and what the potential energy will look like. Start with the potential. So start with right here. And then start with what it have here. Woo, getting it there, right. Right? See if we can sketch the potential energy graph. And then sketch what, look at it, you can even look at the chart on the left. Sketch your potential in the middle and then do it for kinetic. Sketch the potential first, then the kinetic. See what's sketch you have? Boy, stop looking for it and sketch it thing now. Well, why you sketch it thing? So you don't want to look back there for it, you remember if I ever. So why are you looking for it? Right? So at the two points, potential energy is what? At its highest and in the middle. So how the graph will look? Right? The graph will look. The graph will look like that. Shivish, what do you think the kinetic energy graph will look like? What I mean? Come on, son. We have to face the wall. What the graph will look like? Yes. All right, so the graph looks like that. Right. Here's the question, Azaria. The blue is the graph for kinetic, the red is the graph for potential. What does the graph total mechanical energy look like? A straight line where? A straight line like that? Sure. Remember, you're summing the potential and kinetic across the graph, right? It'll be a constant, yes, but a straight line like that, right? When you add up here and here, when you add up here and here, you'll get this horizontal line there. That horizontal line is your mechanical energy. Okay? That straight line there is your mechanical energy. Adrian, are you okay there? Alexia? Amelia, are you okay? Yeah? So this graph showing simple harmonic motion. Are you okay with that? It's still have a little more to talk about. But while we're here, right? you all recognize that this pendulum oscillating with the same magnitude all the time? Why? Has no air resistance, right? It's in a frictionless environment. What would happen if I begin to add friction to it? Right. The amplitude will get smaller and smaller. What is called that? Because you all did this already. Dampen, right? Dampen. So if I were to damp it, I'm going to damp it up here. Oh, by the way, what kind of oscillation is this here? It's called a free oscillation, right? A free oscillation. All the other oscillations have energy being lost. So watch this here. I'm going to damp it up here. Watch what happens to it. The amplitude going to get smaller and smaller. They go a little faster. So it's going lower and lower, getting smaller. Right, more up a large amount of damping. See it now? Right? It's looking like this, right? Right? So that principle is called damping. But when they take energy away from the oscillating system, it's called damping. Okay? Right. But we need a further definition to show that something. We need a further definition to show that something has a simple harmonic motion, right? So let's take a look at this here. I'm going to let's place it again. About 40 degrees, right? Good. Battery on 5%. Right. I wanted to observe something, right? Where is the restoring force the largest? The restoring force is the force that pulling the pendulum back to the equilibrium. Where is the restoring force the largest? At the maximum amplitude or at the zero amplitude? At maximum, right? Because when it's at its furthest, the force pulling back to equilibrium. Equilibrium is the middle. If I allow this to oscillate until all the energy is gone, it will go back to the middle here. It'll go back to the middle here. Right? So the restoring force pulling it back towards the center. The restoring force pulling it back towards the center. You see that? So maximum restoring force is at this point here. That's okay? Maximum restoring force, right? So therefore, what else is maximum at that point? Huh? Energy and something else. Newton's second law. Force is proportional to what? Right, which is? Force is proportional to acceleration. So at those points, acceleration is maximum. That's okay, Zaria? So acceleration is maximum at these points here. Are you okay with that? What else is maximum at that point? Potential and one more thing. And that's the maximum amplitude, right? So therefore, acceleration is maximum at that point, and displacement is maximum at that point. So they appear to be what? Directly related or inversely related? Directly. What about in the middle here? Acceleration is what in the middle there? Probably zero, right? Because the restoring force is zero. So therefore, acceleration is zero. So displacement is what? At that middle point. So therefore, they're directly related. That's okay? Displacement is here, but acceleration acting towards the center. You're seeing that? You measure your displacement from the equilibrium outwards. That's okay? But the acceleration always acts towards the center. So therefore, they are in opposite directions. You're seeing that? So once we can show acceleration is directly related to displacement and they act in opposite directions, what we have is the foundation for a simple harmonic motion, right? So for simple harmonic motion, acceleration proportional to minus displacement. Everybody okay with that? So once a body could display this, it's moving with simple harmonic motion. Everybody okay with that? Timothy? Of course, there's formulas in between, right? But I just want to explain where all this came from, right? Right. Do I show you the graph? All right, let me just with that sine graph and thing as yet. Right? We have some slight bad news. You gotta be able to differentiate sine, cos, and tan. But if you can't, you can learn it all. Right? Sine and cos, sorry. All right, so that's what the graph look like. When I add friction, you know about damping. Right? Let us take a look at this next simulation here. This simulation is with a helical spring. Right? Look at this spring here. All right. Watch this helical spring here. Do you think this helical spring will display simple harmonic motion? Yeah, because we read it, right? And you know it's right. So it should work, right? So let us allow it. Look at the graphs and look at the way it's behaving. So I'll let it run. For those who, if they're sticking, you could go online and do the same thing, right? So you can actually see how it works, right? If I stream in, yeah, I stream in it. So what's your graphs there? What's the energy graph first? Right, let me pause it. How to pause it? Press pause then. Brilliant. Right. What's the energy graph there? You all see the energy graph? K is kinetic, U is potential. You all see the energy graph? So we're getting the same energy graph, right? Yeah? Ariane? Sarah? Seen it? Everybody okay with that? Right. So therefore, it appears to be simple harmonic, right? But look at the graph of displacement, velocity, acceleration. Ignore this, right? We did this one already. Look at the graphs. Can I expand this way? I can't as well. So you can see? All right, well, let's take my word for it, right? So you have displacement, velocity, acceleration. Look at the displacement graph. What type of function that behaves like? Cos. Good try. That's a cos graph. What about velocity? What type of graph is that? Sine. And look at the acceleration graph. It behaves like what? A minus cos. See that? Huh? You all looking the same? You sure? All right, watch. Remember the cos graph starts at 1, right? And the sine graph starts at 0. Okay? So they're not the same. Pardon me, sir? Huh? Which one? Yeah, that's a minus sine graph underneath. A minus sine graph. So what that means is that displacement, velocity, and acceleration, Saraya, right? They have functions that are trigonometric. Yeah. They have functions that are trigonometric, right? The displacement graph has a cos. The displacement graph X has a cos function. Velocity has a sine function, and acceleration has a cos function again. That's okay? So we need to understand the functions and see how to get it. Right? So again, if you watch it move, as the helical spring oscillates, it's behaving with simple harmonic motion. Okay? All those graphs there, we associate with simple harmonic motion. All right? So as it moves, you see in the little, oh, I'll start over. Right? Look at how velocity and acceleration behaving. The proportional but in opposite directions. You all realize that? Look at the purple and the yellow. I'm gonna start over for Shivish and see. I want to make sure Shivish see it. Watch the yellow and the purple Shivish. They're behaving in opposite directions, see now? So they're directly related but in opposite directions. Okay? That shows simple harmonic motion. Are you okay there? Everything we did there is simple harmonic motion. Now it's time to put some numbers and formulas into it. All right? Sorry? All right. Right? When you'll go, you'll play around with the simulation, right? I want you to notice, I know some of you are kind of blindish, but I want you to also notice that here is the equilibrium position. Down at the bottom. Here is maximum displacement, and here is maximum in the opposite direction. Okay? So you're going to see how it behaves. Online, are you okay there? Amelia? Trouble? The light on? The light on? Yeah. You okay with that? All right. So that is your simple harmonic motion then. Right? Let's take a look at the theory behind it now. Right? This handout only has the notes, right? Those who are not on the group, send me a WhatsApp, right? So I'll send you the handout. All right. Right, so I just read in. You can follow if you get lost, let me know, right? In the oscillations of a system, Timothy earlier, I just go into this. In the oscillation of a system, there's a continuous interchange of kinetic and potential when the total energy of the oscillating system is constant, right? Then the oscillations are said to be free oscillations, right? These are not normally observed because there's a loss of energy, all right? Right, here's the examples that we just talked about. Some quick definitions to remember. Period, time for one cycle, frequency, number of cycles in 1 second. Here you have your relationship. F is equal to 1 on T. Right, we have our first new quantity called angular frequency. The symbol is really omega, right? It's not W, it's omega. And it's the number of oscillations in 2 pi. Right, so omega, yeah, omega is 2 pi on T. That looks familiar? From circular motion, right? Right? So you have omega is equal to 2 pi on F or 2 pi on T. Displacement is the distance moved by the oscillating object from its equilibrium position, and amplitude is the maximum displacement from the equilibrium position. All right? What is simple harmonic motion? Simple harmonic motion is defined as the motion taking place in which the acceleration of the object is directly proportional to the displacement, and they take this opposite directions. So I showed you all that a little while ago, right, Aaron? And then remember, when you take the proportional sign off, you'll get a constant. So you end up with this formula here for simple harmonic motion. Okay, we're almost done, right? Right, and this here is graph. That's the graph of acceleration versus displacement. Right? Remember we said it's directly related, but When acceleration positive, displacement negative, right? So the graph looks like this. A straight line like that, right? Huh? Capital E is amplitude. Remember, acceleration is equal to omega squared x naught. Right, so it's minus omega squared x naught. But at the largest point here, amplitude is A. Okay, so that's why it's not x, it's A, right? Here, I just here, look at here. They're ready. Watch, look at the formula there. But it's not a minus here. This is not a minus, huh? In the graph, it's not a minus, right? When the amplitude negative, just positive. All right, and then the graph we are talking about, look all the graphs right here. For those who can't differentiate, this is displacement, this is velocity, this is acceleration. For those who can't differentiate, watch this here. This is your graph for displacement when you start at maximum displacement, right? That's the function for displacement. You all remember velocity is dx dt. So if you differentiate cos, what you'll get? Oh, by the way, we use omega t instead, right? What's the differential of cos? Minus sine. What's the differential of omega t with respect to t? Omega. Right? And then you put back x naught omega t. So that's how they got this here. And then how do we get acceleration? Differentiate velocity with respect to time. What's the differential of sine? Cos. What's the differential of omega t? Omega. Omega by omega is omega squared. And you write back the minus, the x naught, and the omega t. That's how they got this version here. Dx dt. Everything right there, everything right there. Yeah, top one is dx dt. So to go from displacement to velocity to acceleration, we differentiate. All right? And they kind of expect you to know how to differentiate. But for now, if you can't, you can just learn it off. But you'll have to learn up all 6 versions. Huh? When the equation is x is equal to x naught cos t, and when it's x equal to x naught sine t. All right. So those are the equations. That is the introduction to simple harmonic motion. Right? Next day we start back from right here, and we'll go into some calculations that involve